Good afternoon, everyone. This is our final presentation for the wildfire modeling from the Team VCU class collection for the Sallie Center for Mathematics and Biology.
Right, so a bit of background. Wildfires are becoming more and more relevant to our daily lives. With global temperatures on the rise due to climate change, it's only fitting that forest fires are becoming commonplace alongside all kinds of natural disasters. In the United States alone, in 2020, there were 58,950 wildfires, compared with only 50,477 in 2019, according to the National Interagency Fire Center. About 10.1 million acres were burned in 2020, compared with 4.7 million in 2019. So not only were there more fires started in 2020, but the total acres burned was more than double that of 2019. It is more important than ever to understand these natural occurrences so that we may better understand them in the future. All right, so for key goals, understanding wildfires is key to their prevention and containment. So we wanted to create a model that focused on the effectiveness of certain containment methods and that accurately depicted the spread of a natural forest fire. Our many goals and questions changed throughout the duration of the project, but overall we worked to develop our model into the most accurate display that we could. We were always working towards truly understanding the containment methods we used, as well as the patterns and tendencies of the spreading fire based on different factors like plant diversity and density. Realistically speaking, firefighters maximize their ability to put out a wildfire by using a combination of different containment techniques, a few of which are shown in the photos listed. So on the far left, you have an aerial attack, which is where a plane is used to reach hard-to-access flames. In the middle, you see another method called backburning. This is where firefighters deliberately set a small blaze to meet with the main front line of the fire. And lastly, the picture on your right shows firefighters removing combustible materials in a time-consuming and labor-intensive process called fire breaking. The fire breaking method is the one we have chosen to model.
Right, so just to talk about the rule set, I feel like during the first few weeks, kind of not struggle, but we're having some difficulty like trying to figure out the rule set and what direction we want to take our modeling towards, just because it's kind of a broad subject and we just wanted to narrow it down. So we wanted to model our world where there are different kind of vegetation species. So we have brush, shrubs, and trees. And our trees are stationary turtles, while our brush and our shrubs are just patches that have different shades of green, just to represent it. And the main difference between those three are their burn duration, which is 2, 3, and 5 ticks respectively. And we also want to implement a river, which is a natural control line in a way, because the fire cannot cross past it. So this is our little command for the river draw, which after we set up our world, we can manually move our mouse and draw the river wherever we want on our world. But this also comes in handy later when we were trying to, set up our control line where the firefighters put it down. So we're just thinking of like color coding wise. If we want to code something that is not fuel and not burnable, it's not going to be green. So we pick the blue for our control line as well. And then for our firefighters, this is like our little final low for the firefighters, just to be a little bit extra, because why not? So just not as simple as just a regular human shape, and our terrain, which is kind of a big one, because realistically speaking, the terrain kind of accelerates the fire if is a big one, since the fuel are much closer together, and the firefighters will also have a much bigger time to contain the fire if they have to move past like a more difficult terrain. And beside all of this, we have orange patches represent those that are on fire, and then red patches that represent kind of an ember phase before the fire completely burned out.
So here you can see a diagram basically depicting exactly what An just explained to us. So in our world, we have two different distinctions. You're either fuel or you are not fuel. If you're fuel, you are either brush, shrub, or a tree. Our brushes burn up after about 2 ticks, and they are the easiest to catch on fire because they have the most lenient conditions which allow it to catch on fire. Then we have our shrub, which is one more than the amount of ticks it takes for the brush. The brush represents more of a grassy, grassland kind of plant life. And then our shrub is anything between what you would consider grass and below what you would consider to be a tree. And then we have our trees, which burn for the longest amount of time at 5 ticks. And they're the hardest to catch on fire with the most requirements in order for them to catch. And then if you are not fuel, you can either be a patch or a turtle. So our patches that are not fuel can either be gray colored or they can be blue. If they are gray, they represent empty space that is determined at the setup of our world. In this setup, you have a density slider representing the density of the plant life in our world. And say if that slider was at 0.9, then 90% of our world would be fuel, and the other 10% would be this gray empty space to represent real life conditions where you can walk around in a forest. And then we have our blue patches, which are represented as fire lines, which only appear when the firefighters have put down their fire lines by removing the green or combustible materials.
All right, so this is our progress over the weeks. The first square on your left, it took us a while to come up with like all of this just because we want to, do a little bit of research and see how the actual terrain in the world is. So as you can see, there are different color of patches of green that represent, like I said, the shrub and the brush. And then you can see the little pine trees right there, which takes the longest to burn. And of course, the shrubs and brush, we decide to randomly scatter it across our world with the density slider so we can easily adjust it. But for the trees, we have a slider for exactly just how many of trees we want to be in our world when we set it up. And the number of orange patches right here are, since this kind of changed over the time of how we want our fire to start, because I'll explain it as we go. Towards the end, we kind of have a different vision of how we want our fire to start. But right here is at the very beginning, we just want our fire to start like randomly in our world, just like, location wise. So I believe this is the number of patches on fire like equals 11. So, and then the square on your right, which is a lot smaller and looking a lot more clustered, but so our world right now is double the size of the one on the left, is 101 by 101, whereas the one on the left is only 51 by 51. And we also made our patches smaller. And then as you can see, there are a few red blocks, like patches, whatever you call it, that represent the ember phase before the fire burns out. So instead of just going right from orange to black, so it will go orange, red, and then black. And then the little white line right there is our terrain, which when we set up, it's just white turtles. And as we hit go, it will just spread and just create kind of a more complicated looking world like this. And then our progress, this one, I love this picture so much, the one on your left, which is, you can see little firefighters putting down the control line, which is the blue patches. So where they start would be the lower left corner right here, all 12 firefighters we want. And then we code it so now the fire will not randomly start. In a way, it's still random, but it's within a control parameter, like within the center of our world, because we don't want like too much of the random factor for the fire anymore. And then as the fire starts, the firefighters will move towards it. And in our code, there's so the patch will update the firefighter where it's spreading. So the firefighter would try to move towards where the fire is spreading, and then just put down the blue patch. So it just updates it every tick, so the firefighters know where to move. So yeah, this is them putting down. the control line, and you can see an animation in the next slide, which makes it a lot more like comprehensible. And then this is our last tweak of our world. So as you can see, like I said before, where the different green patches represent the different like shrubs and then shrub and brush. Now the green actually represents the height. So the lighter green color represents where it's a higher altitude compared to the rest. So once the fire spread past the lighter green, it'll spread a lot faster, just because I said the steeper the slope, the easier it is for the fire to spread. And then when the firefighters move past the lighter green region, they will move a lot slower, just because realistically speaking, it's harder for them to overcome like the slope or like the terrain. And then they just, we just make it a little smaller, the firefighters, and they also move a little faster compared to the one on your left. And here's a little 3D, moment to appreciate everything. And then this is our run.
So here you can see our 3D version of our model officially running. You can see the firefighters running to the fire. It's not super easy to tell, but they actually go uphill slower, just like in real life, and the fire actually travels uphill faster, just like in real life. You can kind of see in this simulation that the fire will spread past the fire lines, even if the firefighters are working their very hardest. So that was one of the things we really wanted to experiment with, to figure out what parameters will make the firefighters, hold on, we'll watch it one more time because it's that pretty. What parameters allow the firefighters to really contain the fire and what makes them effective. So after having our model up and running, we wanted to do some experimentation in behavior space to see which factors really take the model out of balance. The main factors we wanted to test were plant density and shrub density against the count of blue patches or fire lines that were laid down. If 0 fire lines were laid down, it's very easy to conclude that the fire burnt out before the firefighters could even reach it, rendering containment unnecessary. You can see this in the upper right-hand box. If the amount of blue patches was between 100 and 350, this was considered to be a sweet spot because the fire lines were effective enough to put out the fire, meaning that the containment was successful, but they weren't so effective that the fire went out in just a few ticks, meaning that the containment was unnecessary. Both examples on either end of this range are shown on the left. And then lastly, if we have the number of blue patches being laid down equates to above 350, we can conclude that the firefighters were unable to effectively contain the fire because they continued to lay down these fire lines for thousands of ticks. This can be seen in the lower right-hand box. In our experiment, we saw a maximum count of blue patches to be over 1,300, meaning that the firefighters worked for hundreds of days straight, which is entirely unrealistic. So because of the experimentation, we were able to find the most realistic ranges for these parameters within our world. So you may be wondering, what does all of this mean? There are multiple implications from our findings. Under different conditions, we can conclude that there are infinite possibilities for the spread of a wildfire. Flashing back to those first few weeks when we asked the question, what is the most effective method of containment? We can now confidently say that different methods have different levels of effectiveness based on the conditions of the place that they're in. The use of fire lines may be extremely helpful in a place with more shrubs and little variation in terrain, but it could be rendered useless in a place with mostly brush and a great variation in terrain. When we consider the very generalized questions that we had at the start of this project, we're left only to say, it depends. It depends on where we are, it depends on the makeup of the environment, and it depends on the resources available to these firefighters. With this model, we may not be able to give a single generalized solution to forest fire containment, but we are able to give specialized solutions to specific situations, and we can even model the conditions of a real-life wildfire to predict its behavior and the effectiveness of fire breaking for that fire.
Oh, there are actually a lot of future extensions of the model that we can do, since in our world we kind of assume, it's a perfect world where there's no weather factors that can help or like slow down the firefighters, where in real life, of course, that is a big factor, because throughout our research, I found out that there are wildfires that after a couple of days of the firefighters working hard to put it out, there was rain, and it dramatically helped like change the results. But also there are sometimes wind that did not really help at all and just made the situation a lot worse. And then humidity and thunderstorm can also just strike some lightning and just make the situation a lot harder to contain. And also drought, which is one of the number one, not the number one cause, because one of the top causes of wildfire in the United States. And then we're thinking of, since our terrain right now is kind of random, because we let our turtle kind of like run randomly and just draw different heights in the world, but we can actually think of importing a topography map for high-risk area in the United States, and then we can actually help like understand that specific region a lot more, because as you can see, like the West Coast, and then somewhere in Texas, some in Florida, and some in Colorado, those like are really at a high risk for wildfires. And because like I said, we were having a lot of broad topic, and we just picked kind of a specific direction that we wanted to go in, but there's a lot more factors to this that we would love to explore if we still have the time. So this is, it has been a great pleasure to be working with this team, and especially like giving this topic, given that, climate change is a very big thing right now. And as you all can see, every summer you go on the news and there's more than one wildfires, and it takes weeks to contain it. So it was really interesting that we were able to be able to code this and just like have a deeper understanding of what this is. And of course, big thanks to our mentor Ryan, and then Michael, and of course all of you guys for listening to all of us during the past few weeks and the program itself. So, and this is our citation, but I will go back to the meme because I love it. Does anyone have any questions?
I guess I had a question. By the way, your topographical map was like so awesome, and the simulation, like beautiful, amazing. I'll give you guys a kudos for that. I was just curious, like, because I did think that the topographical kind of aspect was because I was actually surprised, because I remember like when I was watching your guys' presentations over the weeks, it seems to be like a new element. So I was curious about like how you guys decided, maybe like if like the heights were randomly generated, or you had like specific terrain in mind when you were creating, like, I guess like hills.
Yeah.
We actually did have it randomly decided where the patches were going to be the tallest. At the very beginning of the setup, we have it set up so that each patch is asked to be given a random height, and the patches around it have to be within a certain range of that height. If you can see in the slide that we have pulled up right now, the one on the left side, we had turtles going uphill and drawing lines once they got to the top of the hill. So all of the lines are leading to the peaks, versus in our final net logo model, we got rid of the lines and actually did a gradient to show the different heights of the patches, which we thought would have been more visually pleasing.
Thank you.
Thank you.
And visually pleasing it is. These are just gorgeous to look at. I have to ask, so there's this really interesting paradigm going on that you described, where the fire spreads more easily uphill, but the firefighters presumably move more slowly uphill. Is that correct? Was that the implementation?
Yes.
So, based on that paradigm, are there any sort of, I guess, fundamental observations or conclusions for an optimal firefighting strategy based on this sort of unforgiving topography?
Yes, there is. So, because our model, we focus mainly on the containment of fire using fire lines, that is much more practical to be used in a flatter situation, which we kind of mentioned. In a situation with great variation in terrain, that's when the aerial attacks would come much more into play and would be able to reach those flames that are going uphill much faster that the firefighters just can't catch.
Yes, and usually in real life, firefighters usually just use a combination of methods except for one, because when I was doing my research, like there are like more than 10 different ones, and usually they use a lot more than just one. So this is like us just putting down the basis, because for every situation, firefighter would start with putting down the control line, but they would proceed as they view the situation and which one is the most suitable one to treat, like to put out the fire, contain the fire. Yeah, but the control line is most of the time their first step towards containing the fire.